So now let's get into some stoichiometry. Okay, so stoichiometry is basically just a $25 word that means, sorry you guys, that means the quantities from the balanced chemical equation. Right? So before we were looking at chemical conversions or molar conversions, right? Where we were just using one compound. Or atom, element, whatever, right? Now we're going to be looking at chemical conversions with the balanced chemical equation, aka the chemical reaction, right? So let's start off with a, So looking at this reaction, what was the original question? Alex, I'm sorry, what are you talking about what we're doing right now? Or are you referring, oh, the last one. I'll post the video later, so you'll be able to look at it then. Yeah, sorry about that, Alex. Cool. So what kind of reaction is this? Combination, that's right. So we're starting off with two reactants, right? And on the product side, we have one product, right? So we're literally just combining these two elements to make this guy, okay? Now this is a really famous reaction. This is called the Haber process. And this is really famous because it was an extremely big deal in terms of what it did for the population of our planet. So this guy is called ammonia. I'm sure you guys have heard of that before, right? This guy makes up about 80% of our atmosphere. And this guy is pretty dang abundant, right? So being able to use the nitrogen that's in the air to make ammonia is super important because what do we use ammonia for? Anybody know? Gas. For what? Gas. Not gas, but arguably more important. Fertilizer. Right? So I think this reaction was discovered in the early 1900s. Before that, the population growth was heavily limited by the amount of food that we could produce, right? And this reaction is responsible for arguably more than half of the world's population today being able to eat. So it's kind of a big deal, right? Haber was a real dick though. He was not a cool guy. He definitely believed in the Nazis' cause, or not the Nazi, but early German success in World War I, and was a Jew also. and he ended up basically being responsible for chemical warfare in its modern inception. He was like, yeah, let's use chemicals to hurt people, and then accidentally became responsible for Zyklon B, which was the gas that was used to kill Nazis, or to kill Jews in concentration camps. So he kind of accidentally killed a lot of his own family. So, you know, a few million people, MBD. So, yeah, pretty cool. Yeah. To make nitric acid. Yeah, definitely. But yeah, so his chemical warfare started off with chlorine gas. Actually, I think they started with bromine gas and then they went to chlorine gas. But if you guys don't know anything about those gases, they're they're extreme irritants. So basically, when you die from chlorine gas poisoning, you suffocate to get to death on your lung juice, basically. So really unpleasant stuff. There's a good reason why it's outlawed now. But yeah, so Haber, really cool guy, solved a lot of problems and then also made a lot of problems. Anyways, sorry, sidetrack. Let's talk about this equation in terms of balancing. What we think we're going to need to do to balance it.
Multiply 3 the hydrogen, make it 6.
So why 6 hydrogen?
So that way you can multiply the product side by 2, so they both equal 6.
Right, so we're thinking we want to multiply this guy by 2. What's the motivation for that?
So you can multiply the hydrogen on the other side by 3.
So we have 2 nitrogens here now, right? We have 2 nitrogens here, right? So nitrogen is now balanced, right? So now we have 2 times 3 is 6 hydrogens, right? So we can multiply the hydrogen gas over here by 3, and then we've balanced it, right? You guys with me? Cool. So I'm going to take this to the next page so we have plenty of room to solve. Let's say we have 1 mole of hydrogen gas and 0.2 moles of nitrogen gas to start. And we want to know how much ammonia will be produced. Okay, so again, our reaction is, oh, you guys, I'm so sorry. This. Right? So, if you guys are following along in my notes, before we get to solving this problem, there's a couple of topics I want to talk about, okay? The first one is, if you know you have a chemical reaction, right? Chemical reaction is a lot like a recipe, right? So the reactants are like ingredients, right? And the products are the products, right? It's the thing that you make. So before we get into the chemical reaction, I like to talk about recipes because I think it's more intuitive, right? So let's say that I'm trying to make fish tacos. right? And I have a fish taco recipe that requires 2 pieces of fish. Oops. And 1 taco shell to make 1 fish taco. Okay. So do you guys see how this is analogous to a chemical reaction? Yeah? Cool.
Yeah, Alex wrote in the chat.
Oh, so here when we have a 2 out front for the ammonia, we have the 2 applied to nitrogen, but also to the hydrogen, right? So 2 times 3 gives us 6 hydrogens over here. So we need to have 3 times 2 equals 6 hydrogens on this side, right? That's how we balance it. Does that make sense? Thank you. Alex, does that make sense? So this goes back to balancing chemical equations, right? So when we're talking about chemical equations, we have to have the same number of atoms on the reactant side as we do on the product side, right? Because otherwise we made something out of nothing, and that's alchemy, not chemistry, right? So the only way that we can do that is we can't change these chemical coefficients, right? Because that belongs to whatever compound we're dealing with, right? So we can't change the subscripts involved because that changes the chemical. All we can do is write coefficients out front to say that we need this many of this guy, right? Or if there's nothing there, there's an implied 1, right? On this side, we have a compound. We know that 2 is applied to the entire compound, right? So it distributes. So we'd have 2 times 1 nitrogen gives us 2 nitrogens, and 2 times 3 hydrogens gives us 6 hydrogens. Does that help? Cool. Awesome. Any other questions about the balanced chemical equation? This is really good. Cool. Awesome. Okay. So we've got our recipe, right? And let's say we're starting off with 8 pieces of fish and 10 taco shells, right? We want to know how many tacos can we make? Right? So can you guys figure this one out intuitively? I see Jessica figured it out. Cool.
I love fish tacos.
Yeah, me too. This is why I like this example.
Yeah.
Anytime you can, put things in terms of food because it helps, at least for me. Yeah, so I think for most people, it's kind of intuitive that you see this 4 pieces of fish as being the limiting quantity, right? So if every taco shell can make a taco, right, and we have 10 of them, we have more than enough taco shells to make however many fish tacos we want, right? So we could make up to 10 tacos out of our taco shells, right? So the fish, in this case, is the limiting ingredient, right? AKA the limiting reactant, okay? So now let's formalize our understanding a little bit. So instead of just intuitively looking at this, right, let's set it up dimensional analysis style, right? So we use these quantities to relate the ingredients to the amount of product we can make, right? So if I want to get to fish tacos, right, I know for every 1 taco, how many pieces of fish do I need? Is everybody comfortable with that? 2 pieces of fish, right? So I cancel the unit of fish, and now I've got taco by itself, and that's where we come up with that intuitive 4 taco answer, right? Now if we did the same thing for taco shells, we have 10 taco shells, and we know that there's 1 taco shell for every fish taco. Oops. Oops, sorry guys. Taco. There we go, right? And so again, we see that we could make up to 10 tacos using our taco shells, right? But can we make 10 tacos with our other ingredients? No, right? So we would be able to make 4 tacos, right? But what would we have left over? Huh? 6 taco shells, exactly, right? So we would have 6 excess taco shells. Does everybody see how we got to that number? Cool. So in any reaction that has 2 or more ingredients, right, we're always going to have one of the ingredients being the limiting and one of them being in excess, right? Now, I think the idea of something always having to be in excess kind of gets away from us in this example, because you're thinking, well, if I know what the recipe calls for, why don't I just use the exact quantities, right? And that works fine for the recipe, but when we get into the chemical analogy, it doesn't work as well, right? Because now we're talking about measuring out exactly something, and we know when we measure things on a balance, we're never going to get exactly what we think we're going to get, right? Moreover, when we do these chemical reactions, we're not always going to get the reaction to go completely, right? Or it's not always going to be perfect, right? So that's why determining who the limiting ingredient is and who's in excess is always the first thing we have to do when we're trying to figure out how much of a product we're going to form. You guys tracking with me? Cool. Questions? So, in order to answer this question, the first thing we need to do is figure out who the limiting reactant or reagent is. You'll see those guys used interchangeably. Okay. So I gotta switch pages now. And we started out with 1 mole of H2 and 0.2 moles of N2 gas. Is that right? Oops, sorry. Yeah? That what we started out with? Cool. And we want to know how much ammonia we can make. So this how much is kind of a vague way of putting this, right? What could we be looking for when we say how much? I'll get back to you in just a second, Zainab. What unit does that translate to? Could be grams, right? It could also be moles, right? So if we want to make it a little more challenging, we can solve for grams. But in this first example, I just want to focus on how much, meaning moles. okay? So if a problem is vague like this, answer the easier version, right? Not the more complicated version. I'm not going to give you a vague question on a test or a quiz, but in case you see that in problems. So we got to do what we were doing with our fish recipe or our taco recipe. Start off with moles of hydrogen gas, and we want to get to moles of ammonia. So what unit needs to go on the bottom here to cancel?
Is it the 0.2? No.
So whenever we have a unit up top here, right, we always want to cancel the same thing right here on the bottom, right? Does that make sense, guys?
Mm-hmm.
You guys picking up what I'm laying down? Jessica, you look upset.
I'm just confused as why we're doing a conversion right now.
Because we want to figure out how much of this we can make. And in order to know how much of this we can make, we have to convert our ingredients into that and see which one is smaller. Does that make sense? We're doing this.
I was just doing math. I was like, okay, well, there's 3 H2s, so I'll just multiply that by 1. And
Yeah, so this is where we have to get formal with it, right? Because when the numbers are simple like this, you're like, oh, I could probably do this in my head, right?
Yeah.
But when they get more complicated, you absolutely cannot do it in your head, right? So especially when you're starting off with grams of things. So right here we're starting off with moles, right? So that's a relatively simple conversion, just like our original recipe was for the tacos, right? But what we're going to be starting off with a lot of the times is going to be grams of something. If we start off with grams of something, then we have to go to moles, then we have to go to moles of the... it gets more complicated, is what I'm getting at.
Okay.
So grams is a quantity that you can measure in the lab, Alex. Moles are the conversion unit. Right, and this is, you're going to want to go back and watch the molar conversion video. Okay. So that was last Wednesday. So, but we'll do another example in this one, so hopefully you'll at least get a little filled in. But definitely you'll be able to come back to this video and watch this again later. So, we're trying to convert from moles of H2, into moles of ammonia. Right? We need moles of H2 on the bottom to cancel. So, now this molar ratio comes from the balanced chemical equation, right? Or our recipe, as it were. So we have 3 of the H2 for every 2 of the ammonia, right? So 3 moles of this guy for every 2 moles of this guy. All right? So that'll give us that, yeah? Everybody okay with how we did that? Cool. So now we want to see, we start off with 0.2 moles of N2 gas, right? How much ammonia can that produce? So again, we want moles of nitrogen gas on the bottom to cancel with nitrogen gas up there, and then moles of ammonia up top, right? So again, from the valence chemical equation, we didn't write it here, but there's an implicit 1. So we have 1 mole of nitrogen for every 2 moles of ammonia. So who's our limiting reactant? Hydrogen or nitrogen gas?
Nitrogen.
Nitrogen, absolutely, right? So nitrogen gives us a smaller amount of product, right? So this is where our bottleneck occurs, right? Even though hypothetically we could make this much ammonia with that hydrogen, right? Our nitrogen is what's limiting the reactant, or the reaction. Does that make sense, guys? So we would say that nitrogen is our limiting reagent, right?
I have another stupid question.
No, go ahead. What's up?
I'm sorry, because I really do value the conversions.
Yes.
With this stuff, it's really confusing.
Yes.
But, like, can't we just look at it, like, in the example, in the initial question, we see that there's 1 mole of hydrogen and 1 mole, or 0.2 mole of nitrogen. So just looking at that, can't we tell that nitrogen would be the limiting factor?
Nope, absolutely not. So let me change things around for you a little bit, okay? So let's say we started off with 0.4, right? It still looks like this is a smaller quantity than this, right? You agree? I'm sorry, vice versa, strike that, right? So it still looks like 0.4, so 1 mole is greater than 0.4, right? So it still looks like ammonia or nitrogen would be the limiting reagent, right? But what happens when we put a 4 here? See what I'm saying?
I see what you're saying.
This is where it gets non-intuitive, right? So that would give us this, right? Now, this guy is the limiting reagent.
Science.
It's also tacos, really. It's more intuitive with tacos than it is with chemical reactions. Shocker. Right?
Yeah.
So yeah, it's not about comparing these two guys, right? Because this is like saying, which is more, 4 apples or 3 bananas, right? That's kind of a useless question, right? Because they're not the same thing. So what do you mean, more of what, right? Does that make sense? So you have to get them into units of the same thing before you can compare them, right? And again, the initial reaction that you have of 1 is greater than 4, so this, or 0.4, so this must be the limiting, is not a good intuition, right? Because it's hard for us to do these conversions in our head, right? We have to write them down, or at least I do. So, okay, sorry I changed all of this, right? Let's go back to the original quantities. So we had 1 mole of H2 and 0.2 moles of nitrogen, right? So we know that these quantities combined can make, 0.4 moles of ammonia, right? So now that we know how much of the product we can make, right? Let's figure out how many grams of the product we can make, okay? So we're starting off here with moles of ammonia. Right? And we want to get to grams, right? So what quantity do we need to get from moles to grams on the molar coaster?
Molar mass.
The molar mass, exactly, right? So nitrogen is 14.01 grams per mole. And hydrogen is 1.008 grams per mole. And there are 3 of them. So our molar mass ends up being 17 something.
.034.
Yeah. Cool. So, what goes on the bottom here? The molar mass you have to calculate. So the molar mass of the individual atoms, right, you can find on the periodic table. So nitrogen is here, right, and that's what we put there. And then hydrogen is over here, and there's 3 of them, so we multiply by 3 to get the molar mass of ammonia. No worries, Alex, that's fine.
So to start out, we
Yes.
only take the limiting number.
Exactly. So we're not flexing on the hydrogen at all, right? Because we know that the hydrogen is in excess, right? It's not determining how much we're going to make. So we want moles of ammonia down here, right? And we want grams of ammonia up top. And we know that there's 17.034 grams of ammonia per every 1 mole of ammonia. The limiting reagent part is the hard part, right? Mostly because it looks intuitive, but it's not. So what are you guys getting for this one?
6.834.
0.8?
6.8.
Oh, 6.8, gotcha.
336.
And we're good. I'm going to leave it there. I'm lazy. Right? So that would be the mass of ammonia that we could make. Cool. Questions about what we just did here? So this is a lot. I know we only did one problem, right? But it was a lot of information, okay? So the majority of the problems that I posted for your chapter 6 homework are questions like this, okay? So what I would do if I were you guys is right now start trying to do those problems, right? The sooner you try to apply this, the easier it'll be when you come back to it another day, right? So this, again, is combining the idea of molar conversions with balanced chemical equations, right? And the big important definitions that we've talked about are who the limiting reactant or limiting reagent is and who is in excess, right? Occasionally you'll have problems that will tell you you only have this much of this reactant and the other one is in excess, right? If that's the case, then you don't have to find the limiting reagent. Does that make sense? Because they're essentially telling you who the limiting is. So when you're asked to solve for the mass of a product, This is often referred to as the theoretical yield, right? Now, the reason we call it the theoretical yield is because when we do chemical reactions, this is what we should get, right? The law of conservation of mass says that whatever mass we started with, we should end up with the same mass, right? Even though it's a different thing. But that doesn't usually end up happening in practice because we can lose some of our products, we can have side reactions, we can have contamination of our product, stuff like that. Does that make sense? So what we actually get is our actual yield, right? What we get from doing the math here, that's our theoretical yield. What we should get, but we probably won't actually get. Does that make sense, guys? Cool. Any other questions about this stuff? All right, you guys, so I will send out an announcement once there's a quiz posted for the week, and I will put I'll change the exam date so that you guys know when it's going to be. Okay?
Okay.
All right, bye. I love you. I'll see you Wednesday.
Bye.